Welcome to the second video in our Class 4 time series of lecture videos. As I promised in the first video at the very end, we would continue the second video with a summary of the relative stereochemistry for the Diels-Alder reaction. Your text gives some sort of example where you have some sort of generic S-cis diene, where you might have these two outside groups because they're pointing outside away from the diene, and you might have these two inside groups that are symbolized with I that are sort of pointing towards the inside. And then you might have a dienophile, some sort of alkene, where you have endo groups and exo groups. So what do we mean by endo groups? These are groups that are usually electron withdrawing groups that must have pi bonds for that secondary orbital overlap, right? And when we react that alkene with this diene, we like to plug those endo groups in, slide them underneath the plane of the diene or over the plane of the diene. In terms of the relative stereochemical results for that action, and in this case, I have slid the dienophile, this alkene, underneath the plane of the diene, formed my single bonds, and then unfolded it up such that, these interior groups rotated out and they end up both cis to each other. The outside groups rotated in such a way that they ended up with dash bonds, and they are cis with respect to each other, and they are also cis with respect to the endo groups. So hopefully people can see that doing the mental gymnastics. If you can't, definitely ask me during the class time to exercise my artistic work and see if I can draw that out and depict that. That should be fun. Let's take a hard and fast example. Here we have, our diene where our two outside groups are methyl groups, and there are two inside groups that are not explicitly drawn. They are hydrogens. Well, if I slide this alkene underneath the plane of this diene and form my bonds, and then unfold these two carbons, bring it up into the plane, so I have, coplanar 6 carbon atoms in my cyclohexene ring. I've pushed both methyl groups down such that they have a dash, and my methyl ester group ends up down. I could have just as easily slid this alkene above the plane of the diene and then folded it back into the plane once I form my 2 carbon-carbon single bonds, in which case the methyl groups would both be up, and the methyl ester group would also be up. This is simply the non-superimposable mirror image, so the enantiomer of the product that I drew. Of course, I indicated that that product would be racemic, so that means there'd be an equal amount of its non-superimposable mirror image enantiomer. All right, continuing forward with a few more examples. Stereochemistry for the diene. Here it doesn't matter, our alkene has, it's a tetrafluoroethylene, right? And we're reacting with this diene where our two outside groups are methyl groups. The methyl groups both end up on the same side relative to each other, and our product is meso, right? There's a, internal plane of symmetry that cuts right through the molecule. Here's an interesting diene where one of the methyl groups is pointing outside and the other methyl group is pointing inside. And if we react this, we could slide the alkene in underneath the plane of the diene, or we could slide it in above the plane of the diene. As I've drawn it, with this particular orientation, to get this particular stereoisomer, you would be sliding the alkene above the plane of the diene, forming the bonds and bringing these 2 carbons into the plane of the 6 carbons of our cyclohexene product. And if you did that reaction with that alkene on top of the plane of this diene, that methyl group would end up pointing up, and this methyl group would end up pointing down, so having a dash bond. If I had slid the alkene underneath the plane of this diene as it's drawn, that's how I would produce the enantiomer, the non-superimposable mirror image of this particular stereoisomer. So this methyl group would be up, this one would be down. Pretty interesting stuff to visualize, right? And as drawn in my notes, geez, one CH3 group is outside, one is inside, so they end up on opposite sides of the cyclohexene ring. Hopefully you followed along my discussion of how we ended up with this stereoisomer that's drawn, and then how you end up with its enantiomer. If you didn't, be sure to ask me during the class time to go through this example specifically. So a little bit more, and then we'll call it quits for this particular video. The S-trans conformation of 1,3-butadiene does not react in 4+2 cycloadditions. Only an S-cis diene can participate. And that's because if we tried to react the S-trans, we would form a trans double bond inside a cyclohexene, which is simply too high activation energy. It doesn't work. A 6-membered ring won't accommodate a trans double bond. So, geez, only an S-cis diene can participate. And here we have a diene that's locked in a ring, it's conjugated, and it's locked in an S-trans conformation. That cannot be a diene in a 4+2 cycloaddition. How about relative reactivity of dienes in our Diels-Alder? Well, wow, these cyclopentabelline, they are more reactive than, say, this particular conjugated diene with 2 methyl groups both pointing outside, which is more reactive than 1,3-butadiene, which is much more reactive than this conjugated diene with 2 methyl groups pointing inside. So why is that? Why is cyclopentabelline the most reactive diene of this group? And it's because it's locked in an S-cis configuration. So remember, the S-trans configuration is usually the lower energy configuration. So you have to get into the S-cis configuration before you can do the Diels-Alder reaction. And if you're not already locked in that configuration, that takes energy, and so that adds to the activation energy of the reaction and slows it down. That's why your cyclopentabelline reacts faster, because it's already entropically preordered. This particular diene reacts fairly fast because we have electron donating methyl groups. They're both outside. Yes, the major conformation is the S-trans form, but yeah, electronically we're in a good place for this diene to react. This 1,3-butadiene is kind of, it's electron rich in terms of its pi bonds, but all of the groups on it are hydrogen, so not adding a lot of electron density. And while this particular diene has methyl groups that would donate electron density and electronically help with the Diels-Alder reaction, when we put it in a S-cis conformation, those methyl groups sterically repel each other. And so it's difficult to convert this from its major conformer in the S-trans configuration to this S-cis configuration where it can react. So hopefully that all makes sense. I think that pretty much finishes up this particular lecture video, and I'll see you for the next one.